Here's another image that shows some beauty in mathematics. I don't think I can explain exactly what this is, but if you take a dodecahedron is a regular polyhedron that has 12 pentagons as faces. And if you look at the angles are a bit bigger than 120 degrees. So you couldn't put 3 dodecahedrons around each other. No, excuse me. You can put 3. That's a little less than 120 degrees. But you can put 3. They won't close up. But you can't put 4 around because that would be 90 degrees. So what happens? Well, in hyperbolic space, the angles get smaller as the things grow. The angles change. A triangle doesn't have 180 degrees, but the larger the triangle gets, the less the sum of the angles becomes until it tends to 0. So here, these are dodecahedra in hyperbolic space that grew to the point at which the dihedral angles were 90 degrees, and so you can put 4 of them around one edge, and that way you can fill up the whole space with these hyperbolic dodecahedra. But it's sort of an interesting thing to look at to see this. For us who work in geometry, this is very impressive to us. Here's another example of the interaction between mathematics and nature. The bees have learned from many generations that this hexagonal way of filling in space and filling in the plane is very efficient. Let me talk a bit more about mathematical beauty and some comments on it. A Hungarian mathematician, Paul Erdős, very extraordinary person, expressed his views on the ineffability of mathematics. He said, "Why are numbers beautiful? It's like asking, why is Beethoven's Ninth Symphony beautiful? If you don't see why, someone can't tell you." He said, "I know numbers are beautiful. If they aren't beautiful, nothing is." He was a very interesting person. He didn't have a residence. He had 2 suitcases and traveled around visiting one collaborator, one friend after another. When I was a student, shortly after I was a student years ago, they used to say that if you want to find Paul Erdős, you should go to the nearest train station and wait. Of course, there weren't many planes at that time. Erdős also spoke of the book. I don't think he believed in God. I'm pretty sure he didn't. But this was a book in which God would have collected all of the most beautiful and amazing parts of mathematics. He was a very interesting character. I had the privilege of hearing a lecture by him about 10 years ago, just before he died. Here's another comment by a scientist and mathematician, Clifford. He said, "There's no scientific discoverer, no poet, no painter, no musician who will not tell you that he found ready-made his discovery or poem or picture, that it came to him from outside, and that he did not consciously create it from within." This is very lovely. I've had this experience, too, of looking at something that I had done and thinking, I didn't really do this. Beauty is a guide to discovery in mathematics and physics. I'm going to talk only briefly about this, but it's not only a result of known things in mathematics, but it's a guide to finding new symmetries, new truths. The beautiful suggests the true. And this is something that I know from great mathematicians are guided to new advances by the aesthetic sense, by knowing what is beautiful and appreciating what is beautiful before they find out whether it's true or not. I'm not in this category of great mathematicians, but I can observe in a number of the mathematicians I had the privilege of knowing in Princeton or later on, that they are just like a bee goes to a flower to take its essence, they're attracted to new discoveries by beauty. Paul Dirac, great physicist, said, what makes the theory of general relativity, Einstein's theory that explains gravitation, as curvature of space-time, what makes it so acceptable to physicists, in spite of going against the principle of simplicity, is its great mathematical beauty. I'll come back to that in a moment. Here it is. No, right now. Einstein was so convinced by the beauty of this theory of general relativity that it had to be correct. Arthur Stanley Eddington, a great physicist from England, observed the bending of light in the solar eclipse of 1919 in Brazil and in the island of Principe. And Einstein was lucky. In 1917, they tried to observe another eclipse, and the clouds made it impossible. So, but he had made a mistake in his calculations, and in the intervening 2 years, he corrected them. So in 1919, his calculations were correct, and the eclipse showed this result. The presence of the sun between distant stars and the Earth curved the path that light was following. And so the stars appeared to be farther apart than they were. But in order to observe stars with the sun in between them, you can't have the sunlight there. You won't be able to see the stars. So you had to have a total eclipse of the sun, and then you could see that the stars had been spread out. And the amount of the spreading of the star confirmed within a very small error what Einstein had predicted. So someone asked Einstein, what would you have thought if the observations had not confirmed your theory? So he replied, then I would have been sorry for the dear Lord. The theory is correct.
Yeah.
So if God had not understood this and made the theory, it would have been too bad for him. A professor I had at Princeton, Jack Milner, who's still very active at Stony Brook out on Long Island, sees new questions and structures from the perspective of beauty. In having him as a professor, I could really appreciate that. And it was what guided him in his remarkable work. I mentioned something that's not here, a story of another professor I had in Princeton, Salomon Bachner, and he would write an equation on the board of some theory, and then he would turn around to us with an enormous smile that showed how beautiful this was and how he was just completely enamored of his beauty. A contagious smile. So mathematics in the mind of God. What are mathematical subjects, mathematical objects, mathematical concepts? Where do they come from? The natural numbers, 1, 2, 3, and so on, or starting with 0 if you wish, come from our ordinary experience. The need to count coins, or count cows, or count people. So it's natural where they come from. But these numbers have to have a certain kind of existence. You know, you might want 3 to be 5, or 2 plus 2 to be 3 instead of 4, but you can't change it. The numbers have these values, and they are independent of what we might like. So what is the existence that they have? Well, Plato, in his philosophy, thought there was a real world of ideas. Certainly everyone knows that. And that the numbers would be these ideas. They would be among the ideas. But St. Augustine gave a Christian interpretation. He was a Neoplatonist. And so for him, numbers and other mathematical realities exist in the mind of God. The Platonic ideas are in the mind of God.